Okay, we're rolling. All right, lecture two. This is going to be a little more review and kind of frameworking for the rest of the semester. I will try to touch on some C++ that we're going to need for folks who might want a little refresher, or folks coming in from other languages. So we're still doing a little bit of our crawl, walk, run. So bear with me on this stuff. I'll try to breeze over it, not too deeply. But all of these things have links to code. So if you're feeling like you need some review, just kind of save or come back to some of these links and explore the code examples. Or you'll see in Canvas, I've posted the review lectures for our C++ midterm and final exam. So that's pretty brutal. I know that's like a good hour-and-a-half long video each. But if you want a super comprehensive review of C++, you're welcome to download those videos or watch them on double speed, etc. So hopefully that will help you out a little bit. So in about a week and a half, we've got a homework one due. We'll talk about this at length on Tuesday. By the end of lecture on Tuesday, you'll have everything you need to pretty much do this. And many of you could probably figure this out over the weekend if you really wanted to, but we got time. So basically, you're going to write a sorting function and then you're going to analyze it. And that is the most important part because as we're going to start talking today, part of what we want you to develop as a skill is the ability to look at some code or create some counters in your code to assess really how expensive or how inefficient or how efficient your code really is. So that's a big part of this course. And so homework one is not only about writing a sorting function, it's about evaluating how fast your sorting function is if the number of things gets larger and larger and larger, because that's a very common theme. And then we have our quiz one, which is pretty straightforward, really. It's just a lot of basic information. So I think you'll probably be pretty prepared for that by the end of next week. Okay. So objectives for today, I'll just touch on lab one, although I'll tell you right now, I'm going to basically give everybody, 100, or we'll drop the grade. I'll figure out what is the easiest way to do that in Canvas. It is really intended as a very interesting problem. I appreciate anybody who's gone after it. A lot of you got the first part done reasonably well. You started generating permutations. You probably didn't quite have the formatting all right. And a few of you actually nailed it. So appreciate you putting the effort into it. It's always appreciated, and definitely your skills will grow as a result of that. So we'll go over a bit of quick C++ syntax, and then we're going to reintroduce logarithms. Why do we care about logarithms? When I took this class, just like you, but I was in a lecture hall with 200, 300 people, I could not understand why I should care about logarithms in a computer science class. I was still trying to figure out this, and I really don't think they did a great job of explaining it. So I'm going to try to demystify this by introducing the concept in math and then showing you where it comes to play inside of our code. Also, arithmetic series is a very, very easy sort of equation or a relationship we can explore in math that has direct correlation to code patterns that we see. And so we'll explain why that is. And later in the course, we'll start doing a little more math with both of these things. But fundamentally, we just want you to refamiliarize yourself with what they mean and what they look like. And that'll get us to our lab two, which many of you will be happy to know is not a recursive lab. So this is going to be just a simple divide and conquer lab that and I've written most of the code for, so you just got to fill in some code in main, and it hopefully will illustrate our major theme today, which is divide and conquer and logarithms. So one second. Sorry, that door has a problem. Come on in. Okay, so that's what we're going to try to do today. Let's get down to it. So lab one hints. Again, lab one, we're going to give everybody a pass on that. This one was a good one and is a good one. Good one to come back to if you ever want to really sharpen your pencils with recursion. But essentially, let's just ask ourselves a few basic questions about this first. How many permutations are there when you have n things, or let's say 3, 4, or 5? So we didn't really talk about it last time. Here, I'll just pop that door. Thank you. We didn't talk about it last time. Here, you can just put that right there.
You sitting down there before?
But
Yeah.
the number of permutations is going to be factorial. So n factorial, no matter what n is how many permutations you should be able to create. So that count number that you want to print out at the end of your sort of recursive journey in lab one is really already pre-known. We can sort of calculate it ahead of time, or we can do it empirically, which means, just tick the counter every time you print one of those things out. But knowing it ahead of time can provide you with some useful insights. One insight it tells us is how much work we got to do. So at a minimum, you're going to have to do n factorial amounts of work, if you will, in your code to generate this particular solution. So we could say that our computational cost for three things is 6 times something, some cost associated with producing those 6 permutations. Because every permutation is maybe not going to cost some fixed amount of time or some fixed amount of work, right? So what is that thing? We don't know, but we know for 3 things it's going to be factorial for 3, which is 6, right? For 4 things it's going to be 24. For 5 things it's going to be 120. So as it turns out, that question mark is n, right? So the best job you can do is something like swapping n things in order to create one permutation. And you're going to have to create 120 permutations. So if you have 5 things, we would say the cost for your most optimal algorithm is going to be, at best, n factorial times n, okay? So these equations that we're going to start talking about are all generally expressed in terms of the number of things we're working with. In this case, it was the number of permutations, n, and we like to create equations that use n so we don't get all hooked up on just a very specific value of n. We want to have a generalized equation. So this first lab was actually some of the best case code you can write is n factorial times n. And that's a pretty expensive computation to do for large values of n. N factorial gets big really quickly. And in C++, we kind of outstrip the precision of almost all of our variables, even double-sized variables or long-sized variables pretty quickly. So good to know. Those are good insights to step back and think about when you're tackling a large problem. It's like, as an outer envelope, like how bad could this really get, right? N factorial is kind of like, oh, that's a pretty big one, right? So anyway, those are kind of some good insights. Now, there's 2 basic approaches to this. I'm not going to dive too deep on this. One is swapping characters literally in the arrays in any possible way you can. So there's some strategy to that that's recursive. Or as I kind of led a number of you down the path on, constructing a brand new array at every level of recursion and passing that new temporary array down. So both of those approaches are pretty good. Turns out that the swapping approach is the most efficient approach you can take. So if you're just swapping things around and passing down the swapped array, that's probably as good as it can get. But you can get the right answer through this other strategy that we were sort of talking about, this construction strategy. And the idea is basically taking your ABC string and pulling out the A and thinking, okay, I'm going to do all the permutations that start with A. Well, what are they? It's A plus every other combination of the remaining letters, right? And then pulling out the B and saying, okay, well, whatever's left, if we're working with 4 things, that could be, two more things left there. So that's really the idea that we were pursuing with a number of us. A couple of the folks were doing swapping, and that is pretty good too, but it's a little trickier, right? So just to lay out some pseudocode for the folks who do want to continue pursuing this, this is kind of what we were talking about with the construction approach. We're saying, hey, I got some letters here. This is how many I have. And what I didn't tell you, which was a little tricky, was one of the things you kind of need to create is a little scratch pad to carry along with you as you're building up a particular permutation. So if we're not doing the swapping thing in here, we just need to sort of collect some letters here, like we collect an A, then we collect a B at the next level of recursion, etc. So as this number grows with this string here, this number goes down until this becomes a 0, okay? So we're slowly building up a permutation over here and keeping track of the size of both of them. And as soon as this reaches 0, we want to print out everything that's in here and increment the counter. So one of the tricky things about recursion is that no matter what level of recursion you're at, if you just keep passing this ampersand countdown, we can increment that and it'll be remembered at all levels of recursion when we unwind, okay? So certainly this is a tricky little piece of code, right? If the size is 0, that means we've built up a permutation over here. Let me get rid of my scribbles. And it's time to print out that permutation, increment the count, and return to the next higher level of recursion. Remember, we don't just immediately go back to main. We have to walk back up every rung on the ladder till we get to the top of where main is. And we don't really know here how far down we are. We sort of have an idea by using this size value here as to whether or not we've reached the bottom. Now, otherwise, we're going to just start pulling out letters and reconstructing a temporary array of all the letters minus the ith one we pulled out. Okay, and many of you wrote this code and had this code sort of on the way toward working, right? It was probably just these two parts you didn't have and maybe that part there. So good job for everybody who kind of began along that path. It wasn't bad work. It's just we had a little further to go. Okay, so here's just some numbers or letters to throw in. So if we get ABC of size 3, we start with an empty string and a 0 over here. Okay, and our count is 0 permutations so far. So down here, we're going to pull out the A and build a smaller array of size 2 from the ABC. And we're going to put the A as the first letter of our permutation. So we're going to add that into a small perm array, right, that we're going to push down, right? And then we're going to create a temporary array here that just has the B and the C. So it's a lot of work. So you might look at the code when you see the solution. I'll share the solution with everybody next week and think, oh my gosh, that's a lot of code, right? Why do I have to write all that? Well, somebody has to write that code. There's no free way to actually do that stuff, okay? But this is the basic approach to doing it without swapping. And it's not a bad way at all. It just requires a lot of copying things back and forth, and those are really represented as costs. So in terms of the cost to do something like this, it's actually probably quite a bit higher than doing something with the recursive swapping strategy, okay? So I realize that's probably not a huge help for you, but I wanted to just share some of that perspective for you. And I'll give you both solutions on Monday or Tuesday next week, so you can kind of look through them if you're curious about how I approach it on mine. Okay. So don't worry if this is like, holy cow, that's too much, right? It was really intended to be a little more challenging than some of our other labs to get us all thinking early. Okay. And it introduces this idea of dividing and conquering, which we'll kind of continue on that journey. Okay. So let's take a breath and move away from the algorithms for a moment and just review a few key things in C++. And this is really just about syntax. So I kind of hope that you will pick up this stuff as you go. I'm definitely trying to keep it relatively simple, but a lot of the stuff we have no choice but to kind of deal with it at some point in the semester. So I put the review videos up there for you, and I will review these key bits of code right before we need them throughout the course. Okay. So if you need any more help, please let me know. If I could teach this course in 3 languages and not lose my mind, I would definitely do it for your own benefit. But these are the topics I'm hoping in green, especially in the next couple of weeks, I can get you comfortable with in code. So dealing with namespaces, arrays, really low level, the difference between character data type and string, a little bit of pointers, a little references. The modulo operator is so important for algorithms. We'll be seeing it over and over again. and pre and post incrementing and decrementing. That's the plus plus and the minus minus. Those things are going to be a little tricky in this class, different than you've seen them in the past. Using randomness is really helpful for us in this class, so we're going to be using it a lot. And of course, we'll just do a little bit of light math today on the algorithms. The rest of this stuff we'll come back to a little bit later in the course, the gray stuff, but eventually we're going to need pretty much all of this stuff before we get out of here. Okay. So let's dive in quickly and just take a look at these. I'll breeze over the top of it, but you can kind of come back at any time to look at this. So our hello world is, of course, just our main block. And if you're not going to have the using namespace set here, you've got to do that STD before every one of those couts. And the return 0 is optional, okay? So STD is just kind of a dialect. I won't go into the long history of it. I don't love it. That's why I usually put the using namespace up top. Now, for those of you like Java, this is just fun to compare. Like this is what you would do to do the same thing in Java. So a little less code, maybe still some indirection, but Java is a very object-oriented language, of course. So we have a little bit more framework around stuff than we do in C++. Python, it just seems unfair. Like that's all we gotta do in Python, right? Cracks me up every time I look at it. I'm just like, holy cow, man. Life is just too hard for us. Now, this strange little thing right here, ENDL, many of you know it by another name, \n. So if you want to move the cursor to the next line, you can just add a \n into your string, or you can do this mess right here. So you might say, why would I do that when I can do this? Well, in C++, this does something called flushing the buffer. So if your program is crashing and there's some crucial debug information that you want to know, it is going to benefit you to end your debug statements with an ENDL rather than a \n. So that's a nice little trick. So you'll see me do it always, but you're totally okay to use a \n to move your cursor to the next line if you want to, okay? So here's our ENDL with our STD, right? And we'll bring in our namespace here in just a second. But that just moves the cursor to the next line, okay? Here's our namespace. Many of you have seen it. So without the namespace, we call this our scope resolution modifier, okay? So STD tells us the neighborhood that cout comes from. And yes, we have to use it with ENDL as well. And it's so tedious. That's why many of us will introduce this up above main just to abbreviate and have to type less. And I'm perfectly okay with that. But if you go work at Google or Adobe or anywhere and tell them Professor Yates told you to do that, they'll tell you I was a bad professor. So you would never use that in an actual production environment. We're just using that here to simplify our lives because we're focused on algorithms. Yes.
When you do the using namespace, that gets like carried over. If it's imported, right?
Yeah, especially if you do it in main. If you do it in main, it can just pollute everything. Yeah. If you ever go do that on Stack Exchange, they'll just blow you up. People don't like that. So yeah. So there's our namespace. Simplifies the code for us. So just keep that in mind. If you don't see that added, for example, in Program IZ, just kind of pop it up there and it'll make your code a little bit more lightweight on the screen. Arrays real quick. You all had a little peek at that last time. This allocates the space, but notice that it does not initialize the values. We can assume that there's junk in there, and there are cases where maybe it's a 0, but I would not assume that it's a 0. So if you're planning on incrementing those as if they were 0, you really should initialize them to 0 before you go make that assumption, okay? Now here I've initialized everything and I've left out the dimension. That's an option we have. That means we're just going to have these values in there and they're going to be of that dimension. So you'll see me do it both ways there. Just keep in mind, these are junk until you initialize them otherwise. Little light introduction to pointers. So an array is really just the address of the first item. So here what I'm doing is I'm creating PTR and saying that's going to be a pointer. This is the symbol for pointer to an integer. Really, a pointer is just an address in memory somewhere. So we're saying, hey, this is a special data type that holds on to the address of integers. So I can use that variable. Initially, it's going to be null, or we'll assume that it's null for the moment. But if I want to create some new dynamic memory, I can create a dynamic array of integers like this, new int 4. So that's like, hey, create me 4 dynamically allocated pieces of integer next to each other in memory so that we can go work with it and come back later and then delete what it points to. Okay, so notice I intentionally left the arrow there because C++ does not nullify that pointer. It's really silly, but now that pointer is pointing to a dangerous piece of memory. It's like walking through a doorway and falling off the 8th floor. It's really dangerous. We should really nullify that pointer. But that's kind of how we build arrays dynamically when we don't really know in the beginning how big they're going to be. This can be a variable or given to us by a user in some command line argument. There's all sorts of things we could use to decide how big that's going to be. So we'll do a little bit of both. Sometimes we'll know ahead of time how big our array is going to be, and sometimes we're going to do it based on some random numbers, okay? So that we're kind of giving ourselves an honest test of what our code is actually capable of doing, okay? Now, remember that when we have a prototype or a function, we do have to describe the full description of the array argument, for example. And we saw this in our lab 1. But when we call the function, we don't really need to say all that stuff all over again, okay? So we'll see that here in a couple seconds. But I just wanted to point out that this and this are almost identically the same thing. There's some very minor differences at the end of the day. An array is nothing more than the address of the first item in the array, and the square brackets allow us to jump around like hopscotch. Okay? So if you see me using those two different formats and you're like, wait, what is this thing? It really is just another way of describing an array. Okay. I'm sorry that C++ has so many alternate things, but I know we'll run into these along the way. Now, if I want to call a function, there's my array x. Notice I'm not passing int x square bracket 10 into the function call. I'm just saying, hey, put the x in there. But when I define my print array, I do need to define the matching type, right? It has to be int, and it's going to be some dimension here, and we'll use n to describe that, okay? It can be called ARR in the array, but X is what gets dropped into the slot, okay? So just heads up. And I know when we were doing our recursion on lab 1, a number of us got a little confused about what it was like to call yourself, right? You don't need to send this down and this down. We just need to use the names of those particular arguments, okay? So we'll see a lot of that in future code. So I'm going to skip over these, but this is a good exercise. Write a function that sums up all the values in an array and returns it. So if we see a function prototype that has a type over here, that means this thing has better be giving us back some value. So we're going to be expecting a return value from that. That's why we can put this in the middle of a cout statement, because it's going to, of course, give us back a value. If you don't return a value, you will get unpredictable results in C++. Very nasty bug, unfortunately, okay? Now, also we have to deal with typing, right? So here is our sum of array of an integer array. But if I wanted to write a version of this that dealt with double array values, I need to write a whole other version of this function, okay? So there's our double version, okay? So I won't have you do all these right now. I just need to kind of fly over the top of them. So yes, unfortunately, we have to write a flavor of the function for every kind of argument combination that we want to do there. Now, for folks who know Java and know about generics, we can do an equivalent of generics in C++. They're called templates. We won't really get into that in this class to keep everybody sane, but you can definitely kind of do that kind of thing. And if you want to learn more about that, come take my advanced C++ class in the spring, okay? So those are our kind of getting things warmed up. Now, a little gotcha in C++, characters are not strings. So a single quote goes in a character array, a character data type. A double quote goes in a string data type. If you try to mix and match these, you could crash your program or create corrupted data. Okay. So I can say, here's a letter, and there's a single character. \n is a single character, not two characters. The backslash tells the compiler, hey, go get that quirky thing that has no real visible representation. So \n is a weird and long-standing way of representing that invisible return character. So that's really one character right there. There's, of course, our string. And if I try to do this, letter equals quote a quote, it will not work. The compiler will fail because you can't shove a string into a character type variable. Even though it's just a letter A, it's still considered a string because you use quotes on it, double quotes rather. Okay. So a little heads up about that. And I cannot put a single quote H inside of the TXT string. In fact, some compilers will try to convert that for you, but in general, you don't want to mix and match things like that. You want to keep things apples and apples, okay? So just a little heads up for you. Little word about pointers. You got a little time, so this is just a little light introduction. But in C++, when we work with pointers, every variable has an address. We don't really know the address right off the bat, but it has one. It's got to have an address in memory somewhere. So if I want to know the address and have a place to store it, I need to create a separate variable that's big enough to store that whole address. So that's a big number. So if you have a 64-byte architecture, you have a 64-bit address. Okay, bits, not bytes. So here's our big address variable. And if I want to store the address of A in there, I just say big address variable equals &A. Go get me the address of A and put it in there. Okay. So notice this is a star int and this is an int. So these two things are okay. Those are apples and apples. Address of an integer by virtue of that ampersand. So some of you will know this, some of you might need a little reminder of that. So now we have the address over there. So I can either print out the address or I can print out what's at the address using the dereference operator. Cout star PTR says, go get me what's at that address. Okay, yes?
What can you do with that?
Lots of things. So if we pass that address around, imagine you don't know me, but someone says, hey, Professor Yates's address of his house is like, such and such a street name. Now you know where my mailbox is at least, right? So you could go put something in my mailbox and I wouldn't even know. So that's the whole idea behind addresses in C++. We pass around the address, which we call a pointer, but it's really just an address, so that anyone can go to that location in memory and do something. So getting the address of something is a potentially dangerous action because you could do some relative damage if you don't know what you're doing with that address. Okay. So it's powerful, it's very fast, it's a good way to actually, change information where you don't know the variable name at all, right? So that gives us the indirect path to the A, right? So if I say cout star PTRA, I'm going to get a 5 out of that because we hooked up or we pointed PTRA at the A, we would say, okay?
Does an address have an address as well?
Yes, it does. So PTRA itself has an address. So if I had its address, then I have a double indirection. So you could get some crazy, crazy code that way. Yeah, for sure. Without a doubt. So here's just a little exercise. So here's some integers over here. Notice the extra stars over here. Int star PTR says, oh, that's going to be, we call it a pointer, but it's an address. So how do I want to hook these up? It's up to us. Pointer 1 is going to be the address of B, which we draw in computer science classes as an arrow. So I say PTR1 is pointing to B, but I really am just storing the address of B over there. But to simplify our lives, we say we're pointing to it. So we can wire these up in any way we want. And then use these addresses PTR 1, 2, and 3 and forget about A, B, and C. We don't even really need to know about them anymore. Okay. So that's actually how Java and Python do almost everything by default. They are doing things with pointers all the time, and you don't really have to worry about them. C++, not so much. C++, the default is instead of getting a pointer to something, we get a copy of something. And we'll talk about that in more depth as we go along. Okay. Now, that's not really part of algorithms, but it's the reality of some of the code we need to write. So we need to just be aware of it. Okay. So I will come back and review again as we go forward. So I'm going to skip over this page because it's really kind of annoying, but some of these things are just plain old not legal. Okay. I can't put a floating point number in a variable that's expecting an address. The compiler stops us from doing that. It's like, whoa, you're doing something dangerous there. So it's going to do very strict bookkeeping to prevent us from shoving values in boxes that don't belong there. Okay. So if you ever have a compiler bug when you're trying to assign a value, it'll usually say type mismatch or something like that. So you can kind of, you don't have to worry about these so much right now, but these are great little, quiz questions on time that we just sort of see if you can kind of figure out what's okay and what's not. And of course, we have to read these from the top down. We got to figure out, okay, well, D doesn't work. C is an address. So this is an address, so I can copy that over, etc. Right? It's not something we want to do on a regular day, but it shows you can kind of follow through the logic of these pointers. Okay. Okay, so won't dig too deep on that. We're going to use the more modern version of the null. Rather than saying 0 or the capital null, when we want to set a pointer to the nothing value, we're going to say NULLPTR. Okay. So if you see me using that and you're like, what is he doing? I'm just sort of shutting off the pointer so it doesn't send you to a dangerous place. Okay. So we should create a pointer and do this by all rights to make sure it starts out life as null. That way we can do that. Oh, if that thing is null, then, if it's not null, then go ahead and follow the pointer and put something in that box. Okay. So just giving you a quick flash of this stuff. Don't worry too much if, it seems like, it's not something you've seen. Again, you can come back and play around with these things. So here's me incrementing a value at a faraway place. I'm saying, go to this faraway place, get the value, add 1 to it, and put it back to that faraway place. So I'm doing modifications at a location in memory through indirection. Okay. And I'll show you why this is interesting here in just a second. But this is the fundamental piece of code that you kind of got to start wrapping your head around if you're using pointers. Okay. So if I wanted to write a function, then somebody gave me a pointer. This is that idea about going to my mailbox and adding another letter, right? It's like somebody tells you where my mailbox is. I'm not even around. You can open it up and increment the value that's in there. That's what this function is doing. We're sending it a pointer and saying, add something to it, and we're done. And now, of course, that value gets changed back in main or wherever it came from. Okay. So we don't really have to know the name of the variable in order to change it, right? Now, if I didn't have that star on there and it was just an integer, I really just am getting a copy of the value. And I can't change a copy of a value. I can change it, but it's not going to have any effect back in main. But when I get a pointer, I can actually change that value way back in main, which is really useful, okay? And once again, if I want to increment a pointer to a double, I'm going to have to write a special version of that same dang function. And it could be called increment me, but it has to have a different argument set, okay? Here's us calling the increment me function. And in main, we're passing the address of the double and it's coming in. And this is incrementing a variable. So we can pass in the address of a variable all in one line and say, hey, here you go. Here's where Professor Yates lives. Go update the mailbox. Okay. So we'll see this in code. I'm just kind of, throwing this stuff at you a little bit, but you can click into any one of these things and explore it a little bit. Now, most languages don't use pointers in this way. So if you're a Java programmer or Pascal was where I first saw this, we work with something called references. So I tend to describe these things as links back to main. So this is inextricably linked to the variable that was passed in main. So it's called x over here, but when I have a function in C that uses an ampersand for the argument, it's linking these two so that any change to A is synonymous with a change to X. It's like an alternate way we can skip using pointers. So we will be using references as much as we can until we have to switch over to pointers because they're just a little more intuitive. You can kind of see we have some clean code in here. We're not dealing with all that, star reference stuff. Okay. So references are very similar in C++ as they are in Java for Java folks. For Python folks, we'll just have to talk because Python's a little unique in its own way there. But we'll use kind of both systems at various times throughout the course. Okay. So we call those references. So don't worry, we'll come back and review that again before you got to use that in anything particular. Okay. So if you want to swap two strings, here's just a quick example of how you can do that. So we could create there's the swap of the integer, right? So how would we change that to a swap string function? Just change the data type on the arguments, right? And call it in a different way. And change this data type to string as well, right? So anywhere you see the int, you just change it to a string. And Bob's your uncle, as they say. We now have a nice little swapping function. Now, word of warning, there are lots of functions in the C++ libraries called swap. So if you just write a function called swap and call it, you may not be calling your own swap function, even though it's sitting right there in front of you. So I tend to call my swap functions my swap or swap special or something so that I don't accidentally end up calling something else instead. We had some nasty bugs in this class a few semesters back. Turned out we all thought we were calling our own swap function, but we were calling a library function instead. So heads up on that. Good idea to kind of write that one yourself. Or if you're going to write it yourself, call it something else. Few reminders about modulo. Modulo is our friend as programmers. Remember that it always gives us the remainder. So if I'm going to modulo something by 10, I'm always going to get a value between 0 and 9 because you can't get a remainder of 10 when you divide by 10, right? That still gives us 10 possible outcomes, including 0. So 0 through 9 is 10 possible outcomes of a modulo by 10. So it's just that we count from 0 through 9, like with arrays, but we don't really ever see the 10. Okay, so 10 modulo 10 takes us back to 0. So this is a really useful thing when we're working with random numbers because I can say, hey, give me some really huge random number like a billion and whatever, modulo by 10, and now we have a nice random number that is somewhere between 0 and 9. We're going to do that a lot in this class because it is really easy to generate a really huge random number, but we often want to chop it down to be from 0 to 99 or 0 to 9 or 0 to what I'll say is n minus 1, right? So whatever n we put there for the 10, that's going to be kind of the number of things that we're going to get out of that expression, okay? Why do we do that? Well, we're going to use randomness to pick things at random or shuffle things around. It's a really useful thing to be able to do, okay? That's going to crash because that's divide by 0. So just heads up on that. Another little caveat, many of us are pretty comfortable with the double increment for a variable, but the before or after has maybe been a little murky until this point, and that's been okay, but it's time to sort of watch out. So when I say cout a plus plus, I'm going to increment a after we print the value, okay? So that's a little tricky piece of code. It's like, hey, print A and then add 1 to it after you print it out, okay? That's quite different than saying increment it first and then print the value. So we will see things like this, for better or worse, in a lot of code that we use in algorithms class. So this is saying, hey, go to position Q, get the value, put it at position K, and then increment Q for the next loop iteration. So these are tricky little ways in C++, and I think Java too, where algorithms are optimized a little bit more so we don't have another line of code in there. Okay. And getting it on the wrong side can completely break your algorithm. So you have to ask yourself, do I want to pull the value from Q or Q plus 1? Which one am I after here? Sometimes if I haven't had enough sleep, I really have to like step away from the computer sometime when I'm looking at code like that. But we'll unfortunately kind of see that code in some of the stuff that we look at. So just heads up, before and after kind of makes a difference there. So we'll use a relatively low grade random number generator. And hopefully everybody has heard me say this before, but I just think it's so cool. We started counting time for computers at midnight on 1970, right? Most of us weren't around at that time, but that's when we started counting, and we started counting by seconds. And so if you say time null, you're going to get back the number of seconds since 1970. That serves as a really great number that is always changing, that we can use as a seed for our random number generator. So you might recall that when we want to generate random numbers, it's like going to Vegas. Somebody hands you a deck of cards and says, let's play poker. You should say, did you shuffle those cards first? So in the same way, we should shuffle our random number generator before we start picking random numbers out of it. Otherwise, we probably are not going to get a truly random result. So how do we shuffle it differently every time? We use the time. We use the number of seconds since 1970, and that guarantees that if you run your program now and a second later, you're going to get a different result. Now, sometimes we don't want a different result. Sometimes we're trying to debug something and we need it to be the same every time. That's okay. Just pick some integer number and put it there instead of the time, and you'll always get the same number of random generated numbers, right? Or the same kind of random number generated numbers. So x equals rand, or my num equals rand modulo 5. So these are the kind of things we can do. And we can shift that over from the 0 to 4 range to have it be 1 to 5 range by just adding that 1, okay? So you'll see me doing this. If we're playing a game where we want to have numbers from 1 to 5 chosen randomly, I'll do something like that, okay? Just be aware that, like always, your parentheses and how you use them will change the meaning of what's going on there, okay? Without parentheses, the 5 goes over here with that, and then we add 1 to the result. Over here, of course, this happens by itself, and that becomes a rand modulo 6, okay? So just a little parentheses reminders there for you, okay? So we'll do a lot with random number generators. It's a lot of fun, and it's a great way to test your code. So when we say deterministic, like if you were to come in and if you were to go to Vegas and play the slot machines, and every morning they reset the slot machines the same exact way, you'd pretty quickly figure out how to win, like show up around 2 o'clock, or, play it in a certain way. So code's the same. If we are picking random numbers, and we want it to be a truly different every time, we got to scramble the seed, which is what we're doing right here. Okay. So we'll do that quite a bit in this class. So yeah, pick a number, pop it in there, and you'll always get the same poker game, right? Even though it seems random, it's going to be in a very, very fixed sequence of values. The other thing we're going to do a lot of in C++ is loading in data from the user. And when you see the code, you don't have to, know too much about it. I'll help you remember this, because this is not supposed to be about C++. But the cool thing about C++ input is we just use the type of the variable to collect the data from the user. So I always say there's an imaginary user over to our left over there. And if I want to tell them something, the arrows point that way. And if I want to get information from them, the arrows point this way, okay? It's kind of a silly analogy, but That kind of helps us remember, tell the user something, get something back from the user. So what do I want from the user in this case? I want a integer and I want a character. So the program is going to wait until it gets an integer separated by a space or a tab or an enter key, and then it's going to wait for a character. So many times in this course, you may be staring at a cursor and wondering why your program's not running, and it's probably waiting for another character or number or something. So just a heads up, that's what that's actually doing for us. And it's actually really nice. It's a really slick way to actually get data in a formatted way without a lot of troubles. Okay. So that's our CN. And we can, load in other stuff one at a time, or notice we did it two at a time here, right? You can take them in pairs or triples or one, or put it in a loop, however you want to do. Okay. Okay, so that's our CN, or common input. Okay. And the type of the variable dictates what the program's going to wait for from the user. Okay. Okay, now to the math part, and this will go reasonably quick. I think we'll get you done by 6:30 for sure. So logarithms, why do we care? It's not hard, the math's not hard, but let's just remind us all, because I never really liked these things myself. Um, so log base 10 of 100, what we're asking there is, how many times do we have to raise 10 to the power in order to achieve this number? So it's really the exponent we're looking for that equation, okay? So 10 to the second power is 100, so 2 is the log base 10 of 100, okay? So it seems kind of obvious, I suppose, but if we go to a different base, we need to think a little differently. What do I got to multiply or raise 2 to the power of in order to achieve 8? 3. So the log base 2 of 8 is 3, okay? So many of us have seen that stuff, not all of us, but we kind of just have to visualize that exponent there, 2 to the third to the 27. And I'll tell you why it'll be useful for us here in just a second. But so these are all different bases of logs, right? And it's very interesting to be able to ask these questions in code. And you're going to want to do this probably for your lab tonight, okay? Now, we can manufacture the power equation by just saying pow 5 comma 3. That's a nice function that we have on hand in C++. So that's kind of the reverse of that thing right there, okay? But in code, if we want to calculate the log, we have a few useful functions. We can say from CMath, log base 2 of n, okay? How many times do I have to raise 2 in order to achieve n? It could be a floating point number, right? It might not be an integer value. That's the answer that we get, okay? So similarly, we can do a log 10. If we want to do other bases, we can do this trick where we divide the value we're interested in, base 10, by the base we're interested in, base 10. And as long as these bases are the same, we'll get the answer to this, okay? So you don't have to worry too much about that. We're going to be living in log base 2 here most of the time in this course, okay? And again, I'll explain that to you here shortly as soon as I get there. So I won't, dwell too long on this. There's lots of ways to visualize this, but we're really just going to be doing it in code most of the time, okay? So here's our table of, 10 logs. Just let me point out briefly that if you know that log base 10 of 100 is 2, and log base 10 of 1,000 is 3, then at least you know that some number between 100 and 1,000 is going to be 2 point something, right? So we want to develop a little intuition about this. It's going to help us when we're analyzing code performance here in a little bit, okay? Okay, so the powers of 2 are really important for you as coders. So sooner or later, you're going to get to the point where you know that's, 2 to the second, 2 to the third, 2 to the fourth, and that's somewhere between 2 to the third and 2 to the fourth, right? So we'll all get there eventually, okay? Or just think of it this way. Log base 2 of 2 times 2 times 2 is 3. There's your clue, okay? So I don't want to, overdo it here, but not all of us have seen these equations in a while, okay? So here's our log base 2 stuff. Okay, can kind of see again, these numbers can be estimated based on the kind of integer logs of things. Okay, somewhere between the log base 2 of 4 and 8 is, 2 point something. Okay, I promise it'll be irrelevant at some point here in the course. Okay, right now it just seems terribly dry. Okay, so I'm going to skip over this exercise for the sake of time, except to just say, notice that, this is an identity, right? 2 to the power of log base 2 of 8 is always going to be 8. And you might wonder, who in the world wants to know that? But later on in the course, you might find that helpful for solving a few equations, okay? So we're going to do some light math later in the semester. And basically, the 2 to the log 2 of x is always going to be equal to x. It's an identity equation we'll use to simplify some more complex equations, okay? If you pick up any algorithms textbook, you're going to have a chapter on this stuff kind of at the beginning. It's like, hey, everybody, remember this stuff. But the good news is we only use it in a couple places, okay? So we'll come back to that. Now, why? Why do we care about this stuff? So let me talk about a little game. Okay, so anybody want to volunteer for a quick guessing game? Okay, nobody.
I'll do it.
All right, thanks, Graham. All right, so we're going to try to illustrate a point. These are going to be pretty simple points. So if I was to say, guess my number between 1 and 4 inclusive, and I will just tell you correct or not correct. What do you think your worst case number of guesses is going to have to be?
4.
4, exactly. So if n was equal to 4, your worst case scenario, if I'm not giving you any useful information, is 4. Now, you might get it in 1, right? You could get lucky. But if we did this over and over and over and over again, you kind of average out to something in the middle, right? So it turns out that's going to be somewhere around 2.5 in the middle, which seems kind of strange. Okay, but that's what we call the best case, the worst case, and the average case if we did it over and over and over again, right? And I was randomly picking my number, not trying to like game the system for you. Yeah. So this is how we analyze algorithms. We always ask ourselves, what's the worst case, what's the best case, and what's the average case? And a lot of the times people are really only interested in the worst case. So the analogy I always use is if your boss comes to you on a Friday and says, hey, our servers are crashing, we need to get it fixed. How long is it going to take you to fix that problem? I need to know so I can talk to the board of directors. Do you want to like go out on a limb and say I can do that by tonight? Or will you want to play it safe and say I'll have it fixed by Monday? Like that's your worst case scenario is Monday, right? Generally speaking, people want to know the worst case scenario. Like, give me the worst news first, and then we'll analyze where we are from there. So very often with algorithms, we focus on worst case and we skip the other cases entirely because it bounds our problem. It says, oh yeah, okay, well, with that game that Graham and I are playing, with those rules, yeah, N is the worst case scenario. That's the worst number of guests we're going to have. So let's look at a different one. Okay, so different volunteer. In this case, I'll give you some information, higher or lower. Anybody want to give that a try?
2.
Okay. Oh, good. Who's that?
That was me.
Oh, thank you. Oh, okay. Okay. So right. So you're guessing a 2 there, right? So if I was to say higher, you would say what? Okay. And if I were to say lower, you would say, and you'd have it, right? You would have nailed it. So if we play by those rules, we're dividing the problem space in half every time you go to your next guess. And that is a log base 2 type of relationship. So if I have n things, I can figure out the maximum or worst case number of guesses by taking the log base 2 of 4. So why is it log base 2? It's because we're dividing in half. So that was the rules of the game. We just said, well, I'm going to give you higher or lower. Okay. So if you have a million things, log base 2 is a whole lot better of n. It's a whole lot better than n. It's a lot like less time. So if we can design an algorithm that is kind of on the order of log as opposed to n, right, which we would describe as linear, it's gonna finish in our lifetime as opposed to never finishing at all. And that's really the main idea behind trying to come up with an equation description of our code. It's like, well, how bad can it get as n gets bigger and bigger? Okay. And that's the theme we're going to have throughout this whole class, right? So as n gets bigger, the equation for that is still going to be log base 2 of n by the rules of this game. So 8 things, log base 2 is going to be 3, right? Log base 2 of 8 is 3. 2 times 2 times 2. So that's why log just keeps cropping up in these things, right? So no matter how big n gets, we get to use the same equation. And we don't have to, talk about it in terms of individual things. We just come up with a description of the equation for this particular algorithm, okay? Regardless of what n we're actually using, okay? So this is your lab today. So you're going to write a while loop basically to modify the boundaries of search based on a higher or lower kind of thing. So you're going to kind of do all of this automatically in the computer. You're going to pick a secret number and then you're going to try to guess your own secret number. So I'll take you through the code a little bit later on. But notice that depending on the answer, we're going to adjust the boundaries, right? So if we were guessing between 1 and 100 by starting at 50 and somebody says lower, now we're going between 1 and 50, right? So I find the midpoint, I divide the problem in half, and then see what they say again. So we just keep dividing and dividing in the right domain until we zero in, and we're guaranteed to actually get the answer in log base 2 of whatever n is, which in this case is a fractional number. So that means, probably it's going to be closer to 7, but we might get it in, 6.64 on average, right? And that's just because arrays have integer positions. They're not real number things, right? So this is one of the biggest relationships we want you to come away with. We want to design algorithms that are closer to the logarithm divide and conquer kind of situation, which means we always want to be able to divide our problem into smaller and smaller pieces. And that's why recursion is such an interesting and powerful tool. It's a natural way to take something like an array, chop it down, chop it down, chop it down, till we get to a smaller and smaller problem, okay? So that's the big, big takeaway, okay? Because we're dividing things in two. Now you could say, hey, what if we divided that game into 3? What if we said, higher, lower, or middle? And I made you go do the math and divide that range into 3. Well, that would be a log base 3 relationship, okay? So the base can depend technically on the algorithm that we choose, but most algorithms divide things in half and then half and then half again. It's just a cleaner way to code. But you could write an algorithm that divides something in 3 parts and search for it that way. And there's definitely algorithms out there that will do that. Okay? So when we say it's logarithmic, what we're really saying is we're dividing the problem. How are we dividing the problem? Base 2 means in half, base 3 means in 3 pieces, etc. But most of the time, we're dividing the problem in half, okay? And we're asking the questions, worst case, best case, average case. And we could always guess it on the first guess, right? There's always a lucky day. So our best case generally is not that interesting. It's like, well, yeah, you could get it in 1, So here's what our log base 2 curve looks like. So as n keeps getting bigger, right? So this is the size of the problem. The number of guesses, if we're playing a guessing game, flattens out as n gets bigger. That's kind of a good thing, right? We don't degrade as quickly if our algorithm is a divide and conquer or log kind of algorithm. Now, in our first game, we were guessing without any hints. That was a linear thing. As n got bigger, our guess count grew equal to n. And that is a linear algorithm. So linear describes how the problem degrades or how the solution degrades as n gets bigger. So the game that we're playing in this class and in general is kind of trying to come up with the closest known curve that we can all relate to that describes the algorithm we're working on or the solution that we're working on. Okay. So knowing a few names, there's only about 6 of them, and you can kind of get your way past the first tier of an interview, right? Of a computer software interview. Like if somebody says, hey, here's an algorithm, which of these 5 kinds is it in terms of performance? And there's really only about 5 of those, and we'll go through all of those. So most of you are familiar with Desmos. So let me just bring that up here real quick. Get rid of my thing. So Desmos, I'm not a real jockey with this, some of you folks are, but notice I have here my n log n, right? No, not that one. Y equals n log n. Where is it? On and off. So here's somewhere. There we go. That red one there is the logarithmic performance as n gets bigger, okay? This is the log square. You don't see that too often. Here's our linear y equals n. And you might say, oh, okay, well, what are these other ones over here? These are what we call quadratic, okay, and cubic, okay. Now, these are really bad, right? If I zoom out, right, and I say, okay, we're not talking about 10 things or 30 things, we're talking about millions of things. Well, look how quickly things get bad. So here's our linear stuff over, or logarithmic stuff over here. Here's that little linear thing that didn't look so bad in the beginning. And here's our quadratic and cubic stuff. It just blows up. So when we say a quadratic algorithm that won't finish in our lifetime, we mean that seriously. Like if you just redesign your algorithm, you might actually be able to solve something incredibly fast. So, and these solutions are still being found during COVID. I think I mentioned this the other day, like somebody took something from quadratic to logarithmic or thereabouts, right? Something that they've been researching for decades, right? So it still happens, right? It's true. And there's new algorithms being researched all the time. But this is really what we're after in this class, is starting to get to know how do we categorize these things, okay? Usually based on some growth of the size of the problem that we often express in terms of n, okay? Now, if you want to, practice your logarithms, you can just, pull out your calculator, or you can just do some flip card stuff on Quizlet. So this is just, it's not a real hard part of our quiz, but it's coming up in 2 weeks. So a couple, logarithms there. You can familiarize yourself with that. And I'll just point out that every once in a while you read and hear about algorithms that are expressed in terms of the natural log, or sometimes it's notated ln. So what is that? That's just log with this e value, Euler's number, as its base. We won't go into why and when we get into that. That's a lot more theory that we're going to get into in this class. But just so you know what you're reading about, when you see ln, or people says, well, that's a natural log kind of relationship. It's just log base e, right? Instead of 2 or 10, okay? So we'll be throwing that around a little bit later. Okay, one more and we'll get you to lab here in the next 15 minutes. I think we're on track. Now, the other thing is arithmetic series. So this one comes up a lot. And after a while, you'll feel pretty comfortable waving your hands at it. But let's look at some code to start this conversation. If I showed you a for loop like that, that goes from 0 to n, and then I put another for loop in there, y, that goes from 0 to n, and a counter in there, any guesses on the value of the count after this thing is done executing? You can express it in terms of n. Let's assume we know what n is. Any guesses?
N squared.
Correct, n squared. So for every value of x, we're going to have n more loops of y. So it really is going to be n plus n plus n plus n, okay? So we would call that quadratic because it's really going to be n squared. So it's n to the second power, or quadratic is the word we use for that. So we want to get to the point where we can look at that code and go, ooh, that's quadratic. That's not logarithmic. It's not linear. It's kind of not great. Yeah. So we're going to look at some sorting algorithms next week that are pretty easy to implement, but they're kind of quadratic in performance and not a great solution for things that need to go really, really fast. But we want to be able to look at code like that and go, oh, that's kind of a square, right? You got a loop inside of a loop, and they're both going to n. That's not great. Okay, quadratic. Now, there's a dirty little secret about the language that we use. It's far more approximate than when you're in math class. So let's take a look at this loop. So x goes from 0 to n, y goes from 0 to x. That means if x is 0 in the first outer loop, the inner loop doesn't execute at all. So we have 0 plus 1 plus 2 plus 3 if we kind of add up the inner loops. And that is an arithmetic series, if you recall. That is a series of numbers that increase by a constant value. And there's an equation for that, right? You know, ancient people solved that equation a long time ago, right? So we can calculate, when we see a loop like that, we immediately can jump to equation and go, oh, I know how much that's going to cost me in exact terms, right? So let's just briefly look at that equation, right? So arithmetic series, if we have q terms that start with 1 and go to q, then they're changing by 1 every time. And the formula for that is just q times the first term plus the last term over 2. Okay? So for the moment here, I'm using q as the number of terms, and it coincidentally lines up with the last term as well. So I've kind of moved us halfway to our loop analysis here. Okay? And we can factor that thing. And when we do, we see that one of the terms is much bigger than the others, q squared over 2. That is the only term computer scientists really care about when they analyze that code we just saw. They're really looking for the largest order term, and they're throwing everything else away, including the 1/2. And they say, it's quadratic. And you kind of go, how'd you get to that? And like, well, I'm just looking at the larger term because that's the term that dominates the performance over time. So it's very like, if you ask me, it's very, waffly. It's like, but that's not exact. But that's how people talk about these algorithms. They just go, it's quadratic. Well, it's arithmetic, but okay, if we factor out the equation, we actually see that there's a squared term, and we just round things off in computer science and call that quadratic. Okay? So a lot of the mystery sort of goes out the window if you can just find the highest order term and ignore everything else, including the 1/2. And then you're like, you sound good in an interview. It's like, that's quadratic, or that's cubic, or that's exponential. You just look for the biggest term that's going to have the biggest hockey stick on your graph. And that really describes the dominant performance of your algorithm. Okay. So I won't take you through all the math on this, but basically if we're counting the inner loops, the first is 0, the last is n minus 1. So we do the little equation here and we come up with n squared is the highest term. So quadratic, right? That's really what that ends up doing for us, okay? So here is that same thing. We just kind of have to plug and chug the formula and we get the exact number of iterations. So we can know exactly that the count is going to be 28, but it's still what we would call quadratic because we're more or less going to be squaring roughly something based on n, which in this case is 8. So this is how we speak of algorithms. We're not going to spend a huge amount of time trying to, play this game. We want to write some code that does some interesting things. But it is a very important learning in this class to be able to come away with because people want to know, do you understand the language of algorithms? Okay. So if you want to review any of this arithmetic series, you can kind of run some Quizlets on it or look it up on the internet or have a chat with ChatGPT about it. Just kind of get it foremost in your mind because it's going to be hanging around for a lot of the semester. And I'll refer to it a lot. We won't do this plug and chug stuff very much, okay? But you can kind of listen to my description again on Quizlet or just kind of, review that stuff. So with that, let's get to our lab, which I think is a whole lot more doable. So we're going to do the guessing game. We're going to do it in a while loop just to demonstrate that we can do divide and conquer without recursion. It is possible to do it. So we just want you to guess your own secret number. I'll take you through the code here. And we're going to use a while solution. You could use it for if you want We're going to generate a guess that's halfway between, because we want to do this as optimally as we can. Every once in a while, somebody will add some randomness to their guess, and I'll say, okay, that's great and fun, but you want to find the exact middle and divide and conquer in the most efficient way so you can achieve log base 2 performance and prove it to yourself. Like, we want to prove it to ourselves. Okay, so let me take you to the code so you can kind of see. But at the end of this, you should be able to compare your total guesses with log base 2 of n, and they should be pretty close. Okay, you should be pretty close, right, on that, right? You might do better, but you'll never do worse than log base 2. Okay, so let's jump into the code here briefly. And I think I can scale it up. Let me turn that off so I don't burn everybody's eyeballs out here. So let me explain some of my my code. So our n is going to be 1024 by default. So we're going to have 1024, a convenient power of 2 for n. So your logarithm will actually be a nice round number. And then we're going to pick a secret number somewhere in the middle of that using our random number generator. So here we set the seed, we generate a random secret number and add 1 to it. Okay, so there's our +1. So it's going to be not from 0 to n minus 1, but from 1 to n. We print it out, we set our boundaries low and high, and we have a variable for our guess, and we have our guess count. And so you're just going to write this stuff in here, okay? And if you go to Canvas, you can see the kind of output I'm looking for to guide you, but you don't have to hit it exactly, but it should be intelligible. And at the very end, we're going to automatically print out your guess count and the secret value and the log base 2. So you should never take more than log base 2 if you're doing a proper divide and conquer. Okay, so there's no real wrong answers as long as you're not guessing it in quadratic time. Okay, so that's really all it's about. A lot more straightforward, I think, than our lab 1. So again, for those of you who didn't hear, you can kind of take a breather and let that lab 1 go if you didn't get it, or just turn in what you have if you're curious and you want some feedback on it. And I'll give you solutions for lab 1 next week, and we'll talk about this one as well. Okay. Any final questions? Okay, don't come to school on Monday because it's a holiday. We'll see you guys on Tuesday. Have a really good weekend.